thank you for coming for the seminar. We have Milton Jara from IMPA, who will talk about the Stein's method for Markovian martingales. Okay.
Good morning, everyone. So, what I'm going to talk about today is about Stein methods for Dynkin martingales of Markov chains. Okay, so let me start explaining what the Dynkin method, what Stein's method is. So Stein's method is nowadays a very popular way to prove the central limit theorem, among other limit theorems in probability, because it allows us to obtain quantitative versions of this central limit theorem. Okay, so let me just briefly explain how Stein method works. So Stein's method starts with the following observation, which is that a random variable z has law Gaussian of mean 0 and variance 1 if and only if the expectation of a function of this random variable z it's equal to, so okay, let me remember, so we have a prime here, and this is equal to the expectation of z times f of z. Okay? So this observation is actually pretty obvious if one uses the explicit formula of the density of the Gaussian and integration by parts here. You integrate by part f prime, you pass the derivative to the Gaussian, and you get the factor z in front of the function f. Okay? So this is the observation, but what is most remarkable is that if a random variable satisfies this identity in an approximate way, then it means that the law has to be close to a Gaussian. And that's a very simple idea, which is very useful, especially if one asks about the convergence in, for example, in the Kantorovich distance. Okay, so the Stein method is very well suited to prove convergence in Kantorovich distance. Okay, so let me just remind you what is Kantorovich distance. So if you take two probability measures mu and nu, the Kantorovich distance between me and you is given by the following supremum. So all functions whose gradient is bounded by 1, and we take the difference of the integrals with respect to the measures mu and nu. We take the supremum over all those differences, and that's the Kantorovich distance. And the Kantorovich distance is useful for probability purposes because it's actually also equal to the following object, to an infimum. So it's the infimum over all couplings between the measures mu and nu. So let me call it a coupling between these two measures, pi. So it's going to be the infimum of the integral of x minus y pi dx pi dy. Okay? So this is a nice thing because we can relate so a probabilistic definition of this distance with an analytical definition. Okay? So the usual way in which one shows convergence, or not even convergence, but sometimes you don't need, maybe you are not absolutely interested in proving convergence, you're just interested in proving closeness. Okay, so that's what we call quantitative convergence. Okay, so you have a random variable where you think it might or might not be close to a Gaussian random variable, and you want to show that it is actually close. What do you do? One possibility is to estimate the supremum here. Then it's going to be true that they are close in Kantorovich distance. And this has a useful consequence, which is that you can couple these two random variables in such a way that they are close in L1. Okay? So this is the usual way in which Stein method is used is that you solve the so-called Stein equation. So what you actually do is that you solve this equation here. You want to estimate this difference here, where this measure here is the Gaussian measure, and this measure here is your given measure. And so what you do is that you solve this equation here. Okay, so this equation actually doesn't have a nice solution unless you take here the expectation of f with respect to the Gaussian measure. Okay, so you need to have a mean zero function in order for this equation to have a nice solution. You do this, and then you see that the expectation if you are given a random variable x, and you want to compare it with a random variable, Gaussian random variable z, you take the difference, and you see that this is equal to, so you this f is equal to this guy here. The expectation here cancels out, and you discover this is just the expectation of g prime of x minus x g of x. Therefore, if you can control for example, this number here, this expectation here, in terms of the gradient of the L infinity norm of the gradient of f, then you are able to control the distance in Kantorovich distance between x and z. Okay? So this is how Stein's method is used in practice. And it turns out that if you do the computation, this Stein equation has a nice solution, and it satisfies good properties. Like, for example, you can show that the second derivative of g is bounded by the first derivative of f. And that gives you some nice room to play with these inequalities. Okay, so this is about how do you prove this type of thing. So you see, from this, if you apply the formula there, you discover that the Kantorovich distance between x and z. Okay, so when I write this, I mean the log of x and the log of z is less or equal than the sup over this is smaller or equal than 1 of the expectation of g prime x minus x g of x. Okay, so this is about Stein's equation. So it's probably very different from the way you've seen convergence proofs of the central limit theorem. You can actually prove the central limit theorem with the rate of convergence using this scheme. It's not very difficult, and it's very interesting because it's very different from the usual proof that one is used to with the characteristic functions maybe and this type of techniques, and it's quantitative. And that's always the nice thing about it, is that it gives you a number. If you estimate things properly, you get a speed of convergence. Okay? So this is a quick overview of Stein method. So now let me make some definitions about Markov chains. So now I'm going to take a state space omega. I'm going to call L the generator of our Markov chain that is going to have the following form. So L f of x is going to be equal to the sum of the rates at which, so these are going to be continuous time Markov chains, so instead of probabilities we have rates. This is the rate at which you jump from x to y, and then you have the size of the jump in f when you do this jump. Okay, so this is how the generator acts on a function f, and I'm going to define a family of operators gamma L, which are generalizations of this generator here. So this operator gamma L is going to be, so this is what I call the Lth order variation. It's actually a very simple thing. So instead of looking at the size of the jump in f when you go from x to y, you look at you look at the Lth power. So and here L, it's a natural number, and you can observe that actually gamma of 1 is equal to L. So this is the generator of our Markov chain, and for simplicity, I'm going to assume that omega is finite. But if you take care of the summability issues, everything works in infinite state spaces. So now I'm going to talk about what is the Dynkin martingale. Okay, so the Dynkin martingale is the following. So you take a function f that depends on time, and it goes from the state space to R. Okay? And I'm going to assume that the function f is differentiable in time. Okay? And then I'm going to define a process mt, which is the Dynkin martingale of f. So I'm going to define mt of f so maybe I can say that I'm going to denote by xt the Markov chain. Generated by L on the state space omega. And then the following object is a martingale. So this guy here is a martingale, and this is what I'm going to call the Dynkin martingale associated to the function f. Okay, and then in general, so this is a classical technique in Markov chain. So you have an observable of a Markov chain. So the observable is a function f, okay, of the Markov chain that goes to the real numbers, and you want to prove some limit theorem, like for example, some central limit theorem. You suspect that this function is going to be Gaussian in some limit. And then a popular way to try to prove that is to write down this martingale equation and somehow to show that maybe this is small or this is controllable in some way, or it satisfies a functional identity. So it's a function of f again. And this guy here is a martingale. And being a martingale, you have classical theorems that tells you that martingales are close to Brownian motion. Okay, so this is the usual way in which you show this type of theorem. So one of the steps is to prove that this guy here converges to Brownian motion or to a Gaussian random variable or a Gaussian process. Okay, so then the question is, how do we do that? I was puzzled about this, so maybe I can give you some reference here. So there is something called probability service. So this is a journal that publishes surveys about different subjects, and there are two probability surveys about, at least two, about Stein methods, which are very good. So one of them is by Nathan Rose, and the other one is by Ley, Reinert, and Swan. So they explain in more detail this the Stein method, and in particular, Jacine Reinert, she has various papers, very interesting papers about how to apply this Stein method in very different situations. But one situation I was puzzled about was kind of not really considered in the literature, was this particular setup here, which is very important for the type of probability we do, which is take a Markov chain, take an observable of a Markov chain, and construct the Dynkin martingale. You want to prove that the Dynkin martingale converges or is close in some sense to a Gaussian process, to a Gaussian random variable. It turns out that there is a very simple criterion using Stein method that tells you exactly that. So let me write down the theorem. So this is actually the theorem I wanted to present. I'm going to take a function phi, which goes from 0t to 0 infinity. Okay? That's just given. So let me take my notes and write down exactly what I want to do. So Okay, so these are just numbers that you can maybe estimate. Okay, so this gamma 2 here is actually the quadratic variation, the instant quadratic variation of the martingale MT, that it should be close to the variance of the Brownian motion to which this martingale should be converging. Okay, so this number phi t should be the variance of the Brownian motion. It might depend on t because the function f depends on t. And this is something you suspect it might be okay or not. So how big this number gamma 2 is going to depend on your ability to estimate that thing there. And in particular, that depends on the ability of choosing this constant phi here. And then you find these numbers, and then there exists a constant c which is universal. So universal means that does not depend on anything. It actually only depends on the law of the Gaussian random variable, which depends on the law of the Gaussian of mean 0 and variance 1. So this is the theorem. Okay? So you see there is no limit in this theorem. It's just a bound. Okay? It is true for every Markov chain, for every function f, for every function phi that you put here. And of course, the bound can be bad, no? There is where your ability to find the right Markov chain, the right function f, and the right function phi here enters into the game. So I'm not going to enter into all the details of the proof. I'm just going to give you the start of the proof. Afterwards, everything is more or less canonical. It's just long to write it, but it's very simple. Okay, so sketch of proof. Yes?
So in the gamma 3, there is no sign. Well, gamma 3 minus and plus can compensate. So if it's the definition of gamma 3, you put an absolute value, can you get rid of the gamma 4 in your expression? Or?
Yes. Yes. But okay. So the question was that so in gamma 3, in the definition of gamma 3, there is no absolute value here. So in particular, there could be cancellations, and these cancellations actually could be useful to get better bounds. But if in gamma 3 there are already no cancellations, maybe you just put an absolute value here. And if you do that, and you use only the definition with gamma 3 here, you can forget about gamma 4 here. That's correct. And it comes very clearly from the argument. So in general, you expect to have cancellations here. That's the general thing. When you go to gamma 4, you see that this is already positive, so there are no cancellations. So those cancellations are important if you want to get sharp bounds. And so about this theorem, so what I like a lot about this theorem is that so it's not super original. There are some theorems. In particular, there is a paper by Roberto and what was the name of the co-author? He was my classmate in the master, so I should remember the name. But yeah, Belloni. So Belloni and Oliveira, they have a very similar theorem about martingales, but it's about martingales. So you have a martingale that doesn't necessarily comes from a Markov chain, and you look at the quadratic variation of the martingale, and there are some criteria, so some numbers that allows you to estimate the same thing as here. So the distance in Kantorovich distance between the law of the martingale and a Gaussian random variable. But what is nice about this thing is that this particular theorem is very well suited for Markov chains. So you plug your favorite Markov chain, you make some computation, and you discover that it is surprisingly sharp. And so how do you prove this theorem? It's not very difficult. So you start with the function f in C4. Okay, so I want the function f to be bounded and all first 4 derivatives of f be bounded. And what we are going to take is that we are going to take a function g, we're going to construct a function g, which is a solution of the following equation that I'm going to call Fokker-Planck, which is just the heat equation backwards in time. So you see that here the sign is wrong of the heat equation. That means that there is a heat equation backwards in time, which means that you have to put a final condition instead of an initial condition. And what we're going to put is as a final condition the function big F there. Okay? So remember that if you want to estimate this Kantorovich distance, what you really want to do is to compute the expectation of a function big F applied to the martingale M. That's our goal, and that's what we are going to try to do. And we are going to use this function g as a test function. Okay? So let me take a random variable zt with law Gaussian with our target variance. Okay? So that's the variance that appears there. You can observe that the expectation of the function f with respect to this random variable is actually equal to this. So it's g of 0, 0. So how do you compute this expectation? You just solve this heat equation, and this is in line with this idea that this was somehow the instantaneous variance. So here in this heat equation, you put the instantaneous variance in this position here, which is where the variance goes actually in the heat equation. It depends on time, but that is okay. You can check that this is actually true. then so the idea is to use the Dynkin formula for maybe I don't want to write it. So I'm going to use Dynkin's formula for the following object. Okay, so I'm going to use the formula that I wrote there, no? I'm going to write the martingale associated to that, but instead of using little f as a test function, I'm going to use this big function g. So this function g depends on time and depends on the martingale. But the martingale MTF is written there, so it's the following formula. Okay? So this is actually a function of something which is differentiable and our Markov chain. So you can still use the same formula here. Okay? So the idea is that you use Dynkin's formula for this. You compute the generator applied to this function g composed with f, and you start to do Taylor. So you start to do Taylor a lot of times, so 4 times in total. So you use Taylor formula up to degree 4, and then you start to collect the terms. So if you do that, there is one term that the linear term cancels because there is a generator here coming from here when you take the derivative, and there is a generator when you do Taylor in the coordinate x in the function g. So the second term doesn't cancel, but in the second term, what is going to appear is the difference between these two guys. The second term is going to be a function of this third order variation, and the fourth term in the layer expansion is going to be a function of the fourth order variation. I'm not going to do the computations, but at the end of the day, what happens is that the expectation of f of MT of little f. So this is a martingale, so it has mean 0, so you take expectation here, and you do the Taylor, etc., and then you discover that the expectation of that guy here you discover this, no? Okay. Yeah, so probably I'm not going to enter into the proof. Maybe it's more interesting to make an example. Okay, so Once you have observed this fact here, the proof is elementary because you start to compute what is the action of the generator on that function g, and whenever you have a difference, you use Taylor expansion, and then this type of objects are going to pop up. So let me do an example. So this is the simplest example I could think of, which is it's just the Ehrenfest urn. So in the Ehrenfest urn, so there is a number n. So the state space is just the non-negative numbers, integral numbers up to n. And then what you do is that our Markov chain xt, it can go to xt plus 1, or it can go to xt minus 1. So the rates at which this happens, so the idea is that in the Ehrenfest urn, you have a box divided by 2, and there are particles here. And each particle wakes an exponential time of rate 1, and it decides to change side. So xt is the number of particles on the, let's say, on the right box. Then it goes to xt minus 1, which is the easiest one, with rate xt, right? Because it's rate 1 for each one of the particles. And then it goes to x plus 1 with rate 8n minus xt. Okay? So that means that the generator, it's equal to this number here. Okay? So you can check that xt, so let's assume that x0 is equal to n divided by 2. Okay? So let's assume that n is even, so we don't have to decide where to put the extra particle, and let's just start with half and a half. Okay, so just to make things simplest as possible. If this is true, one can verify that xt divided by n converges to 1/2 for any t bigger than 0. So the fraction of particles is always 1/2. This is very easy to see because actually, so the invariant measure of the Ehrenfest urn is the binomial law of parameters n and 1/2, and therefore the mean is n divided by 2, and the variance is a square root of n divided by 2. So once you've seen this, it makes sense to define psi of t, which is going to be square root of n. So, okay, let's write it like this. xt minus n divided by 2 divided by square root of n. Okay? So this is the scale at which you should see fluctuations. So we expect, and it's not very difficult to prove, that this thing here converges to a Gaussian process, which is called the Ornstein-Uhlenbeck process. So in particular for each fixed time t, it converges to a Gaussian random variable. And now the idea is to use this theorem to check whether we can prove this in a quantitative way. Okay? So you can check, so L of the function x, okay? So if you take L of the function x, you see that it gives you this minus this. So it's n minus 2x. Okay? So this implies the following. It implies that if you look at L of psi t, so psi t is x minus a constant divided by square root of n. So here, because of the difference, the constant doesn't really play a role. So what you get is n minus 2xt divided by square root of n, which is actually minus 2 psi t. Okay? So this is what happens when you apply the generator to this function psi t. This means the following. Now, if you do this, this gives you 0. Okay? What does it mean? It means that so this object here, m of t, depends on n, divided by psi t e to the 2t, is a martingale. And it's actually a Dynkin martingale. Okay? So now let us compute the numbers there. Okay? So we have to compute gamma 2 of psi t e to the 2t. So this is equal to what? So this is a square, no? When you do the computations. So if you put here gamma L, what you put is an L here and an L here. That's what you do. So there is a 2 somewhere, so there is e to the 4t. And then when you look at psi, the difference here is, so when you look at x, the difference here is 1. So I want 1 or minus 1 to the square, the sign disappears. But there is when you look at psi, there is a square root of t dividing. So you have to square it, so you get an n. And then you get the sum of these two things here, x and n minus x. So it's times n. So it's e to the 4t. So actually, gamma 2 is 0, right? Because I'm going to take phi of t equals to e to the 4t. Then this difference is just 0, so there is nothing to do. Well, we have to compute the sigma. So sigma t squared is the integral between small t and big T of e to the 4s ds. So it's equal to e to the 4t, 1 minus e to the minus 4 big T minus t. Something like that, okay? Then gamma 3. So there's going to be an e to the 60. I'm going to have n to the 3 over 2. Remember that here there was a plus 1 and a minus 1. So there was a plus 1 here and a minus 1 here. So now you get n to the minus 2, n minus 2 xt, which is minus so this guy here had to divide the square root of n, so it's minus 2 e to the 6t divided by n times psi t. Okay, so let me go here because for the moment I don't want to throw away the theorem. So you see that the expectation of gamma 3 is less or equal than, so here you have psi t, okay? So it's not difficult to show that the moments of psi t are bounded. Or it actually follows from this equation here. So I'm going just to assume that this guy has found a bounded moment. So this means that this is going to be smaller than a constant that depends on t. I'm not going to enter into the merits of what is the constant that goes here. You can carry out the dependence in t. And then gamma 4. So there is an e to the h t. We have n to the square down there. And now these guys are plus 1 plus 1. You have the sum is n. So this guy is e to the ht divided by n. As you have may notice, maybe, yeah.
I'm a bit lost in the computation, but I wanted to ask this question. This gamma 3 and gamma 4, they don't seem to be homogeneous. Well, they don't seem to be homogeneous in the sense that if you multiply f by a constant, then the right thing is to multiply phi by a constant. Then gamma 2 is multiplied by this constant, but gamma 3 and gamma 4, they seem to have the
So if you multiply f by a constant, this guy goes to constant square, constant cube, and constant to the 4. And then if you go here, to these powers here, they have the right homogeneity. You get this, the constant square here, the constant cube to the 2/3, another constant square, and the constant square. So they do have the right homogeneity. That's why these numbers appear here, these exponents. Yes, but you multiply by a constant here, then you have to multiply by a constant here too, the constant squared. Which means that here you get one constant less, here you get one constant less, and here you get one constant less too. So okay, yeah, they do have the right homogeneity. One has to do it properly, but they do, and that's actually. When you do the computations in the proof using Taylor, etc., it's important to have that in mind so you don't throw away terms with the wrong homogeneity. But yeah. So, okay, so our question was whether these guys here, gamma i's, have the right homogeneity in the sense that if you want to multiply the function f by a constant, then you multiply n by a constant and this guy by a constant, so this should be multiplied by a constant. And so here in gamma 3, you see that there is already a cancellation because I'm using the fact that this psi has finite moment and psi is already a fluctuation. So let me write this as a constant times smaller or equal than a constant that depends on big T divided by n. Okay, so I'm not going to enter into the details of the depends on T, but what the theorem says is that the distance in Kantorovich between the martingale at time t and a Gaussian of, so you have to take t equals 0. So it's 1 minus e to the minus 4t is less or equal than a constant that depends on big T. So you have to check that the integrals are integrable, but that's okay. I'm not actually worried about the T dependence. I'm more worried about the N dependence. So the N dependence then is what? So the gamma 2 was 0. Gamma 3 was basically 1 over N. So you get here 1 over N to the 3 over T. And here you get 1 over square root of N. Okay? So this is more or equal than a constant that depends on T times the maximum between 1 over N to the 2 over 3 and 1 over N to the 1/2. So we get a bound of the form C of t divided by n to the 1/2. So this bound is actually sharp. Okay, so this is actually the right bound, 1 over square root of n. Right? Because we see that you divide by n, you go to a constant. You divide by square root of n, you get the fluctuations. So the original number was a constant plus a fluctuation of order 1 over square root of n, plus something of order 1 over n. That was the theorem said, and this is actually the right thing. And so let's say that you don't do this, you don't use cancellations here in gamma 3. Then if you don't use cancellations, you will get here, instead of n, square root of n. So when you do this, this to the power 2 over 3, you get square root of n, you get n to the 1/3. So n to the 1/3 is bigger than square root of n, so you don't get the right order here. Okay? So I think my time is basically over. So let me stop here and just thank you for the invitation and thank you for the audience.
Thank you very much. Very nice talk. Is there any question or comment?
I have a question. So this is weird. So talk to me. To which Milton are we talking?
Yeah.
The other Milton. So hi Milton, how are you?
Hey.
Thanks for the talk. Was great. So I have a question. So these bounds are for fixed t. So if you want to prove the functional central limit theorem, you still need to prove the functional limit theorem on the one hand. On the other hand, you use this to have like bounds for each t. Is that right?
Yeah. Yeah. So in principle, there are versions of Stein's method for functional CLTs, but I'm not particularly fond of them because usually the bounds are not that great. But in principle, something you can do if you are interested, if you can do 2 times, or yeah. So for example, not 2 times. So you take the martingale at time t1 and at time t2, and that should go to a Gaussian vector. And well, the same idea, the same strategy also allows you to prove this type of bounds for that. So you can get a finite dimensional convergence if you want to.
Okay.
Which, in principle, it's. I think it's already nice, no, because it's quantitative finite dimensional convergence, not just convergence in law.
Good, thank you. I have another one. So do you think these techniques can give bounds, like for example, for random walks in random environments or things like that, or?
So for random walks in random environments, so there is this trick that I did there. No, that I chose the example because what in random walk in random environment should be called the corrector is very easy, no. So it's always about the ability that you have to pass everything to the martingale. And so the idea is that in random walk, random environment, it's not always the case that the random walk it's a martingale, no. So you want to write it as a martingale plus something. Usually you first write it as a martingale plus the corrector, and then you can write the corrector as a further martingale plus another term. And this nowadays is getting better understood, no. And in that case, you can go on with this methodology to prove convergence of those martingales to the corresponding Gaussian random variable.
I see. I see. Thank you.
Is there any other question? Okay, I have a question. So, Milton, this you have this Ehrenfest urn, and you start with a fixed configuration with half particles in each urn, right? But then at time one, you are not still in equilibrium, right?
Yeah.
Because you are looking at time t, say.
Yeah.
So but you are in this example, you are in some sense proving speed of convergence to equilibrium somehow. Is that right?
Yeah.
Because equilibrium will be the normal thing. The binomial approach is the normal.
Yeah. But I mean, here you can do two things which are, I think, are interesting. The first one is that, no, exactly. You can show, for example, you can try to show that in the Ehrenfest urn you converge to equilibrium so something like obtain something like the mixing time of the Ehrenfest urn is of order n log n or something like that.
Yeah.
You can try to do it with this because this is very quantitative, no? So in that sense is pretty good.
Yeah.
But another thing that you can do is that, for example, you can start not with the proportion 1/2, but you can start with, let's say, all particles at one side, so far from equilibrium. Then you go to
much farther, yeah.
Yeah. So then you go to a Gaussian random variable, which is still far from equilibrium. And you can actually also prove convergence to that Gaussian at some different times, which is not the Gaussian that it's the end of the story. So because what you expect is that if you start far from equilibrium, no, the density goes gradually to 1/2, and if you catch your process when the density is around, let's say, 3/4, there should be a Gaussian fluctuation around 3/4 as well. And this is something you can also access with this methodology.
Yeah. Also, you, in the first case, you also have somehow dynamics of the variance, right? Because
right.
You are getting. Yeah. Okay. So, and what would be the exact approximation for just one normal random variable of your first blackboard? So you have a sum of independent random variables with finite mean and variance, etc., and then converges to a normal random variable, say 0, 1.
Yeah.
And what is the distance you are talking about? Which distance are you talking about there?
Kantorovich distance. So it's it's the infimum.
But it's no time here. No time.
Yeah, there's no time.
It's just variation. The variation distance.
Yeah. So yes, total variation. Yes. So in that case, what you can do is that you can imagine that the sum of IID random variables is actually a Markov chain.
Oh yeah. No, but it's not really. Yeah. No. Okay, you can do that. Yes.
Yeah. So then you
consider it as well. And you are taking the Cesaro mean, I mean, or something, the time mean, the time statistics, the empirical time statistics.
Yeah.
Okay.
Yeah.
Okay. So what do you get? What is the limiting of the total variation distance of the two?
Okay.
If you did it, I mean.
So yeah, for going. So you need something a little bit more, no? So if you want to have total variations, so when in Stein method there is a lemma, no? That it's about the ability to solve the Stein equation. So if you can solve the Stein equation in the uniform topology, then you have estimates in total variation. And well, that's what you.
I don't want to interrupt, but you're supposed to start soon.
No, actually,
no, we are finishing.
You're finished. I came an hour late.
Yes,
exactly.
You are very welcome anyway.
I'm sorry I missed it. I was looking forward to it, but it's recorded. I apologize. I thought it was at
No problem.
5 Portugal time, and
yeah, that's yeah.
Oh, apologies.
Yeah, it's perfect time. Yeah, it should start. Isn't the distance can one hear me?
Yes, Sundar.
Isn't the distance 1 over square root of n for the IAD case?
It is 1 over square root of n, but not in total variation. If you want to get total variation, you need to assume that the random variables are have density or something like that, no? Because otherwise you don't have total variation. So in Kantorovich, it's 1 over square root of n, and then you can also prove Berry Essen with Stein, no? Also you get the 1 over square root of n. But I mean, what I find interesting is that if you apply this thing to hydrodynamic limits, to fluctuations of hydrodynamic limits, you get also the square root of n speed of convergence, which is for me surprising because it's in hydrodynamic limits. It's somehow it's a high dimensional problem, no? And but you still get the right speed of convergence.
And the dimension doesn't come in because, you know, the central limit, the rate of convergence of the multivariate central limit theorem, the dimension comes in, right?
Yeah. So yeah, of course, comes in, and I'm cheating when I'm saying that, because what we do is that we actually look at the low dimensional projections of high dimensional Gaussians. So for these low dimensional projections of the high dimensional Gaussians, we get the right speed of convergence.
Great.
Because of course estimates deteriorate very quickly with dimension, but still they don't deteriorate as bad at one.
They might.
Yeah.
I had a question I was going to ask, and I can ask it if I'm allowed.
Yeah, yes, of course, yeah.
And not interrupting, but Stein's view of Stein's method, there are many different views now, but Stein's view of Stein's method was a basic underlying thing that allowed Stein's method to go forward was an exchangeable pair. So yep. If you have and an exchangeable pair is with which, you know, you have a set and you have a measure on the set and you want to prove some kind of limit theorem about the measure, and so you need an exchangeable pair with marginals the measure that you're generating from. Now, an exchangeable pair is exactly the same as a reversible Markov chain. Yeah, I mean, it's exactly the same thing. And so, and, you know, martingale, well, I mean, that's the linearity in the Stein. So it seemed as if it was related to, you know, classical things which are done in discrete time, but that doesn't bother either of us. And I wondered if you'd made that connection between sort of, the classical machinery, which many people have written about, but me in particular, about exchangeable pairs, and of course the linearity condition in Stein is makes life easier, and that's kind of like a martingale. So I wondered if is it connected or it's completely different?
Yeah, so it's connected in the following way. So I had this this problem, which was I was at the origin of this thing, which is that is the following. So imagine you have the Curie-Weiss model.
Yeah. Okay.
And for some reason you put in one half of the space you put one field H1, and in the other half you put a field H2.
Okay.
So somehow you break exchangeability.
Uh-huh.
So I read your literature, especially I read a lot of Chatterjee's works about it.
Sure. And he and Keyman Chow have a nice paper about Curie-Weiss, right? Getting the e to the x to the fourth limit.
Exactly. So I read all of that, and I say, okay, well, there should be a way to connect this exchangeability thing with the things we were doing, and I tried very hard to do that, and I couldn't do it. So at the end of the day, inspired for everything I read, I actually proved this different theorem that actually gives the answer in my case. So in a sense, my theorem it's a byproduct of my inability of make the connection explicit.
Well, that's so I have no excuse for asking any more questions. I have to go back and watch your talk, but I really am sorry I missed it. I don't actually have to figure out because it did say it's 5 in Lisbon now, right? And isn't that right? And on the website it says 5 o'clock. So 1700. Okay.
Yeah. So it's so I think the safest is always that it's 1 o'clock in Brazilian time. Okay. Whatever time changes in any place of the world, it's always 1 o'clock in Brazilian time.
Very good. I'll remember that. Anyway, sorry and hi, and I'll let you go, but I'll go look on the web and I'll report if I have any comments.
Exactly. Feel free to ask anything. Thank you.
Okay. Is there any other question or comment? Okay. If not, we continue next Wednesday at 13 Brazilian time, right? So, bye.
Bye.